The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and thank you for attending our February webinar, Rheology Tools, Identifying, Understanding, and Handling Data Artifacts. Today, we will be hearing from Dr. Stacy Elliott. Dr. Elliott attained her extensive experience and rheological knowledge through her education at Carnegie Mellon University and Princeton, as well as her experience at both Alcon and DuPont. We're very excited to have her presenting today, and now I will go ahead and pass it over to you, Dr. Elliott.
Thanks, Eden. Hi, everyone. Welcome in today. As Eden just mentioned, we're going to talk about artifacts, data artifacts. So this is going to fall under our Rheology Tools series. So information that can help you handle and get the most out of your data. And what we're going to talk about is how we can identify these different artifacts that can occur, understand why they happen, and then determine whether or not there's some way of handling them. Because in some cases, you can correct for them. In other cases, you kind of have to accept that they're happening and there isn't really a correction path. However, even in that instance, it's still valuable to understand what is happening because it is telling you something about your material and then also how that material behaves in a particular flow configuration. So let's get started. So what we're going to cover today is I'm going to give you a reminder about viscosity because, and I think I probably say this in almost every webinar that we give, and that is that viscosity, it's defined and then it's a calculated property. So viscosity is never directly measured, it's calculated. And so that means that you're using equations that were derived based on certain assumptions. And we're going to go over what the relevant assumptions are. And you see these artifacts come about when these assumptions are not met, because your instrument will almost always give you a number, unless you're overloading the system. So in our case, that would be overpressuring our sensors, or for a rotational instrument, that would be going over the torque, the upper torque limit. In that instance, things will shut down and you won't get a number. But other than that, you'll almost always get a number from your instrument and your software because it doesn't know, it's unable to tell whether or not these assumptions that go into the calculation are met or not. So that's kind of our responsibility as rheologists to make that call. So what are the artifacts that we're going to talk about today that come about when these assumptions are not met? The first one will be secondary flows, more commonly known as turbulence. The next one would be apparent wall slip. And then we would talk about what types of things you can see when you're dealing with yield stress materials. So in the case of a yield stress material, if you're not familiar, this is a material that can support a certain level of stress before it begins to flow. Also viscous or shear induced heating. And then although in the advertisement I promised to talk about some other inhomogeneities, I think we're already going to be a bit too long. So if you want to look at some other interesting artifacts that can pop up due to inhomogeneities in your sample, due to polymer that goes into solution very slowly over the course of days to weeks, I'm going to direct you back in time to a webinar that we gave in January of 2019, where we were looking at stages of polymer dissolution and the types of interesting artifacts that we saw on our microfluidic MEMS technology. So sorry to not talk about that today, but I think we're going to have full time with the other topics. So as I mentioned, we're going to talk specifically about we're going to remind you about the calculation of the viscosity, and we're going to do everything today specific to our VROC technology. However, there are analogous calculations and equations and dimensionless groups that would apply to, say, rotational instruments. And I'll kind of point out some directions if you don't use our technology, but rather use rotational rheometers. Okay, so as you know, we have the microfluidic channel with the MEMS sensors placed along the base of the channel so that we are getting a pressure drop. We're controlling flow rate through the channel, and then we're measuring this pressure drop across the channel. And our controlled flow rate and our pressure drop that we measure go into the equations that we use to calculate the steady shear viscosity. So these equations, we don't make these up. These are derived. And they're derived based, as we said, on specific assumptions. And I have our diagram here to sort of help understanding what some of these assumptions are. So we have this is the visual of our flow field in our microfluidic channel. And what we're representing this as, then, these arrows represent the velocity, magnitude of velocity at a particular spatial point. And so what you can see is the first thing is that this is represented as a laminar flow or unidirectional flow, where all of these streamlines, these velocity vectors, are parallel, moving in the same direction. Okay, so that's one assumption that we're making to use the equations that we do. Second one is that we have what is referred to as no-slip boundary conditions. So solving conservation of momentum equations, it's a boundary value problem. So we have to define what is occurring at the boundaries. And in this instance, the boundaries are the two solid walls that make up our microfluidic flow channel. And the no-slip boundary condition is that we go to zero velocity. The fluid has a zero velocity immediately adjacent to these solid boundaries. So that's the second one, the no-slip boundary conditions that we need to meet for our equations to be fully valid. And the final one that's relevant to our discussion today, I'm not giving you all the assumptions, just the ones that are going to be relevant to the abnormalities that we might see, is that our sample is homogeneous. And that means it's homogeneous in composition, so there's no phase separation occurring on a significant length scale that's going to matter. And it's homogeneous in terms of temperature distribution across the channel or even along the length of the channel. So those are the three things. So now let's understand how these artifacts we're going to talk about relate to these assumptions and the assumptions specifically not being met. So the secondary flows or the turbulence, this comes from the violation of the laminar or unidirectional flow assumption being met. And we'll talk about the details of that. That's going to be our first topic. Apparent wall slip actually has kind of two assumptions that we're violating. So first off, what can happen when you have this apparent wall slip is it is technically an inhomogeneity. It's just on a smaller length scale than you're used to thinking. And it's really specific to the boundary area. And this inhomogeneity in the sample, and it's going to be common when you have these larger length scale objects. So you won't see apparent wall slip if you're just measuring the viscosity of a simple solvent or buffer, because these are very tiny molecules. You have a pure system, one component system, and the surface roughness is large compared to the molecular size, and you won't see it. But when you have something like polymers, colloidal suspensions or colloidal dispersions, microemulsions, anything with larger length scale objects and a multi-component system, you can have these inhomogeneities near the boundary, and you can get this apparent violation of the no-slip boundary. And we'll go into more detail in a minute. Yielding materials, again, you're kind of having the same issues, is that as the material goes through the yielding process, it's going to have some kind of inhomogeneity in it, where perhaps part of the material along the length scale of your test will have yielded, but not all of it. And then it's also common in yielding materials to have slip at the boundary, because yielding tends to occur in these complex fluids that I just described as it relates to the wall slip. And then the final topic would be the shear-induced or viscous heating. And this, again, is going to be inhomogeneity in the sample, but in this case, it's going to be a temperature gradient that occurs. Okay, let's start with turbulence or secondary flows. So on the left, we have what we typically draw when we do our viscosity review, and we're looking at the flow field or velocity profile in our flow channel. And as we stated before, these are all velocity vectors. They're all parallel, all moving in the same direction. So laminar unidirectional flow. What can happen, however, depending on the nature of your material in combination with the flow conditions, is you can have this transition to turbulence. So now this is a much more chaotic state. And now we have streamlines that aren't parallel at all times. They're not moving in one direction. And then you can also have the presence of these eddy currents that exist. And so this is going to be, this is what we mean by turbulence. We're going from the unidirectional flow to this more chaotic state where we have velocity in different directions. And we're going to talk about that specifically in the context of our technology. Now, you can have turbulent secondary flows in rotational instruments as well. And when we get to the more detailed analysis, you can handle it in a very similar way. But we're focusing on our technology for our discussion here. So in our case, we have two types of flow channels. We have our uniform flow channel, which we use for steady shear measurements, and then we have our flow channel with a hyperbolic contraction, which we use for extensional measurements. And the onset of turbulence is going to depend on the geometry. And intuitively, you may look at this extensional flow channel and say, yes, I can sort of see why this one would be more prone to this particular type of artifact, where you have this rapid constriction and expansion. But in either case, as we evaluate when does turbulence come about on either of these flow channels, we're going to turn to the same parameter, and that's the Reynolds number, which we've talked about before, but we're going to talk about it in a little more detail than previously. And this is the non-dimensional group that predicts this transition from the laminar flow to the turbulent flow. So the Reynolds number in general, let's start what it looks like in general, and then we'll talk about how to apply it to those two specific flow channels that we have. And you can actually take the general form and apply it to the other types of geometries that you might be using, such as in the rotational instruments. Okay, so as we said, the Reynolds number, it's a dimensionless group, and it's composed of different characteristic values or scales is a term that we use a lot with this. And although we're not going to derive it in this way, the Reynolds number naturally falls out when you're non-dimensionalizing the governing equations in fluid mechanics. So that's conservation of momentum. So if anyone who's taken fluid mechanics and looked at the conservation of momentum equations and actually gone through the process of non-dimensionalizing them, you'll know that the Reynolds number falls out from this process. And you can get the Reynolds number, the expression for it that way, but there's another way to look at it, which if you're not familiar with those equations might be the better path. But you can actually get the Reynolds number by looking at the different terms in the momentum equation and taking them as a ratio. But a more general way to do this is that the Reynolds number is the ratio of the inertial forces to the viscous forces. And you can kind of think about this, that these inertial forces are tending to drive towards this chaotic state, and the viscous forces are tending to damp that and prevent it from happening. So if your viscous forces are significant enough, then you won't have this transition. They'll kind of damp those that drive towards the chaotic behavior, and you won't have the transition to turbulence. So the inertial forces, so this should be familiar to everyone, it's just mass times acceleration. And as I've discussed, we're looking at the characteristic scales for our material and our particular flow configuration. So that's what the subscript C means. It's a characteristic scale, and L, if in this case, is the characteristic length scale of our geometry, and U is the characteristic velocity scale, and T is just time. So we can get this particular inertial force in terms of all of these characteristic scale values. And then the viscous force, this should be familiar to everyone as well. So we have viscosity times shear rate, so that's just the viscous stress. And then we need an area to multiply by. And so again, we just get this, simplified down into all of these characteristic scales. And so that gives us then, all we need to calculate the Reynolds number are our fluid properties, so density and viscosity. And then from our particular flow configuration, we need to get the characteristic velocity and the characteristic length scale that's appropriate. So let's start with our standard flow channel, where we use this to get the steady shear viscosity. And So in this particular configuration, the first thing to point out is that the transition, the sort of a ballpark figure, and if you go look this up in the literature, you'll see some variability in these values. I've seen 2300, 2400, 2500, because it's really more of an empirical number. Over the years, people have observed at what Reynolds number do you start seeing this transition. So there is some variability there, but this is a good value to target. Once the Reynolds number gets above 2300 roughly, then we can start to be concerned about the presence of these secondary flows. So let's calculate the Reynolds number for our particular standard uniform flow channel. So now in this case, what we need to get then are our characteristic values. So our characteristic length scale in this case is the hydraulic diameter. So this is just how you this is how you get the characteristic length scale for something that has a non-circular or rectangular cross section. And it's just related to the cross-sectional area divided by the perimeter value, the length of the perimeter. And the characteristic length velocity scale, rather, we can get from our volumetric flow rate and the cross-sectional area. So we can put all these in here, and you can see that it's all in terms of parameters that we know. So as an example of something that, when you're dealing with a different type of measurement system, you can expect to see some turbulence. Let's see what happens when we're flowing this through our microfluidics. So we're just going to look at water, something near room temperature, a warm room temperature. So we know the density, we know the viscosity here, and we're looking at specific flow channel characteristics for our E02 flow channel. So 20 micron channel depth, 2000 micron channel width, and operating at the max flow that we could expect for the particular pressure sensors here. So this gives us a shear rate of over 2 million. So when we calculate the Reynolds number for this particular situation, we can see that the Reynolds number is slightly more than 300. So this is we're not going to see turbulence. Turbulence is going to be very unlikely in this particular situation. And in fact, I've never actually had the case where I've seen turbulence in our standard flow channels. You might see, in previous positions where I've worked a lot with rotational rheometers, I have seen turbulence. For example, if I was trying to measure water in a cuvette or cup and bob geometry, and in that case, the reason for that is that the characteristic length scale there is going to be the gap, which is going to be a 1 millimeter generally, or 1000 microns. So since Reynolds number then is proportional to the characteristic length scale, which in that case would be the gap, you're going to have a higher Reynolds number, and you're going to see the onset of some turbulence in that type of flow configuration. So bottom line is, this is how you're going to approach trying to see, if you should expect turbulence in our flow channels. And the fact is that for our particular, the microfluidic nature of our flow channels is going to make it highly unlikely that you'll see turbulence in the standard uniform channel. But this is how you would calculate for your particular material and convince yourself that that is the case. Okay, so for the extensional channels where we have the hyperbolic, contraction, and expansion, this is very different. So I have sort of the schematic here defining what these particular characteristic values are for this channel. Now, we're starting with the same Reynolds number form, but we have a different velocity, characteristic velocity, and our hydraulic diameter is going to be a little different because we're going to be focusing on this constriction area. So here's how these particular characteristic scales are defined. Hydraulic diameter is defined in the same way in terms of the cross-sectional area divided by the perimeter, but now we're focusing in on this constriction width rather than just the channel width. And then the characteristic velocity now is related to the length scale associated with the constriction, the length of the constriction here, and then the extensional rate. So extensional rate is just related to the velocity gradient that you have as you which is now parallel to flow as you enter this constriction. So now we can get, again, the Reynolds number in terms of things that we know. We're controlling flow rate, and we know our material properties, and we know the well-defined dimensions of our flow geometry. Now, the thing to point out is, because this is very different now, we have a very different situation with this constriction. And empirically, what we see is that turbulence now will start to become a concern at a much, much lower Reynolds number. And so now we're talking, 2 orders of magnitude lower, somewhere in the vicinity of 10. We can, potentially see these secondary flows. And although we haven't, hinted upon it quite yet, the manifestation of this turbulence or secondary flows with respect to your data is essentially either a shear or, in this case, extensional thickening. So it looks like your sample is either shear thickening or thickening under the extension rate, but this is not true, because what's happening is, you can imagine that when you have all this chaotic flow where now we're not moving in a single direction, this is going to bump up, it's artificially going to bump up the stress, but it's not related to, the true viscosity, it's related to the flow field being in this chaotic state. So let's look at some data just as an example. So as I said, I don't have an example of turbulence in our standard flow channels. I don't think we've ever seen it. And if anyone's worked with our systems and you think you've seen it, definitely let us know. But I do have an example of turbulence in our extensional chip. So here's an example. We have some xanthan gum solution. So these are just high molecular weight polysaccharides. And we have them, the top curve here, or the top plot rather, is the extensional viscosity as a function of extensional rate. And the bottom is our shear viscosity as a function of shear rate. And we just have 3 different solutions at different concentrations. So what we see then is, they initially thin under both types of flow fields. But in the case of the steady shear, this thinning just continues on up until we get to our max flow rate. However, when we look at the extensional viscosities, we see this point where it starts to turn up, and it looks like we have extensional thickening. Now, extensional thickening is not as uncommon as shear thickening. However, it's always important to sort of take a look at, do the analysis and say, okay, is this a real thickening under extension, or am I seeing some sort of artifact potentially due to the turbulence or secondary flows? And, based on the Reynolds number that we calculate here, I'm highly suspicious that what we are seeing here is this apparent thickening due to the turbulence or secondary flows. And you can see that the higher the concentration of the xanthan gum, which then translates into a higher viscosity, which is going to translate to a higher viscous force, which again acts to dampen this transition to the turbulent or chaotic behavior. We see that the transition to this apparent thickening shifts in terms of the extensional rate as we ramp up the viscosity. So again, another little hint that maybe that's what we're seeing here is this what looks like thickening, but is quite likely due to the secondary flows. So you want to look at this and say, here's a good example of looking critically at your data and saying, it's always exciting to have unique rheology behavior, particularly something that's thickening, but you have to ask yourself and do the analysis and say, is this real or is this an artifact? Okay, so let's move on to our next topic, and that would be apparent wall slip. So to understand what we mean by this, we're going to again look at our velocity profiles, and on the left, excuse me, is the profile that we always present when we're talking about viscosity, and it's clearly illustrating our no-slip boundary conditions, where the velocity of the fluid immediately adjacent to the wall goes to 0 because we have stationary boundaries. Now, wall slip means that the fluid velocity adjacent to the wall is not actually going to 0, and you have some non-zero velocity of the fluid immediately adjacent to the wall. And they generally sort of define this slip behavior in terms of either a slip velocity, which is the value adjacent to the wall, or as a slip length. And this slip length comes from basically extrapolating your velocity profile to the point where you would have a zero velocity. So this is what we mean by slip. And this is actually a situation, and we're going to go into detail about this, where you can actually correct this problem. Like, we can't correct the turbulence happening. We can only identify it and acknowledge it, that it exists. We can't, for given material and flow conditions, we can't necessarily, stop that or correct for it. However, this is a situation that we can correct for. So let's talk about, why do we see wall slip, a little more detail about what is happening there, and then how do we handle it. So I think, as I mentioned in the intro section, slip is not going to happen if you're dealing with solvents or buffers or simple fluids of this sort, or even, standard oils. It's going to happen when you have more complex fluids, typically things that are multi-phase with larger length scale components. And, you can see it also in something like a polymer melt. The mechanism is a little different, so that in that case, it isn't multi-phase, but you do have larger length scale objects that are entangled and can, disentangle and create some sort of inhomogeneity near the wall surface. But I don't want to go into, there are many situations where you can get slip, but the general idea is, you need these larger length scale objects, either a colloid or a polymer or an emulsion droplet or some sort of self-assembling system that forms a gel. And and then what will happen then is you'll establish some sort of inhomogeneity that occurs near the boundary. And the reason this can happen is that, when you're dealing with these low, very small length scale, say solvent molecules, and you're comparing the dimensions to the surface roughness of the boundary, and it looks smooth to us, but in reality, there is some sort of roughness associated with it. It's very easy for, these tiny molecules like water or an alcohol, something like that, to, get stuck in these in the, asperities on the surface of the boundary. However, when you have these larger length scale objects, in some instances approaching a micron, these are much less likely. It's much, well, not necessarily less likely, but there's a bigger chance that these won't get trapped in the roughness associated with the wall. And so what will happen is you'll get, let's take the case of a multi-phase system. You'll have a very thin layer of, say, your solvent, and then adjacent to that, you'll have these molecules which aren't really adhering to the wall. And so this is sort of how that slipping layer comes about. You have this thin layer, such as your solvent, then that has a very low viscosity, and this, generates this large viscosity gradient, or that should be velocity gradient. I'll correct that. Large velocity gradient in that thin layer. That's a typo. And then adjacent to it, you have these larger objects moving, at a speed greater than 0. Now, in this case, we can correct for this, and we can determine what is the true deformation in the bulk material. And I've kind of hinted at how we're going to do that. And you can do that. So in our case, we have the rectangular cross-section. So what we're going to vary is the channel depth. So we look at flow in different flow channels with different channel depths. However, if you're dealing with circular cross-section capillaries, then you would change the radius of the capillary. But that's what we're going to do here, is we're going to get our viscosity versus shear rate measurements, and we're going to get the data as we vary the channel depth. And so we have a variety of flow channel depths available to us so that we can do this. And I'll point out that if you are doing this with the capillaries with circular cross sections, where you have to be concerned about entry or exit effects. So we don't talk about this a lot, and I don't want to confuse the situation, but we don't have to worry about, in our particular flow system, entry or exit effects, because our sensors are placed in the channel and the leading and trailing sensor are spaced at an acceptable distance from the entry and the exit. So we don't have to do any corrections for entry or exit effects, the Bagley correction. But a lot of the other types of capillary viscometers, you would have to do that particular correction, and you'd want to do that before you try to handle the wall slip. So when you're doing certain corrections, you need to do them in a particular order. But in our system, you don't have to worry about that. I just wanted to point that out in case someone does work with those. Okay, so let's talk about the correction when we do have wall slip in the rectangular slit type of geometry. So this is a very, so we have some equations here, but I don't like to just give you the equation. I want to sort of explain how it comes about. And this is pretty straightforward, I think. So if we look at, the average viscosity that we have in our flow channel, we have some apparent value that we're getting, and we know that this is related to the true value plus some sort of slip that's occurring near the wall. But these are inconvenient, average velocity is an inconvenient property to try to deal with. It'd be better if we have something else. So let's go and try to relate this to shear rate, which is something that we can easily work with. And so we know the relationship of the shear rate to our volumetric flow rate and then the channel dimensions. And then we can relate this further to this average velocity. So these known relationships can help us take this equation to something that we can more easily work with, and that is dealing with the apparent shear rate that we get. The software gives us this, and then the channel depth. So what we want to do then is, so the way I've got to this final equation is I've just taken this sort of known balance that we have and converted everything to shear rates. So, well, with the exception of this particular term, because what I really want, I want to keep it in terms of something that we're varying. So now we're going to vary the channel depth, and we know what our apparent shear rate is from our output. So what we're going to plot then is this apparent shear rate versus the channel depth. And we're going to plot this, each of these, plots that we make will be for a fixed wall stress, which we also know from our software output. And what this gives us then is we can extrapolate to get from the intercept what the true shear rate really is near the wall. And that's how we're going to be able to correct our data. And then once we do this plot at a particular fixed stress and we calculate the true shear rate near the wall, we can calculate the true viscosity, knowing the stress, now knowing the true shear rate. And also point out, since I was talking earlier, there are different corrections that you need to do in these capillary type viscometers. I mentioned we don't need to deal with the Bagley correction, which takes into account the entry and exit effects. We're talking about the slip correction, which is the Mooney correction. And so this is the one you want to do next. So you do this correction before you then go on to the WRM, which would account for non-Newtonian behavior. Okay, so let's look at an example for our data. So here is a typical type of a plot that you would have. So now we're looking at apparent shear rate as a function of 1/h. And we're going to do this, as I said, each of these curves will then be done at a particular stress. And we can see how these, how we can then extrapolate to the intercept and then get what is the true shear rate for this particular flow. And then on the right-hand side, we've introduced the corrected viscosity data along with the viscosity data at the different channel depths. Now, one of the things when you're doing this, oftentimes you're going to have to interpolate to get all of these data points at a fixed stress value. And so, maybe, ahead of time, I don't think our data was best suited for this, and my interpolation may not have been the best. So you want to kind of get as many points as you can if you're trying to do this process so that your interpolation is better than mine was. That's just kind of a tip that I would recommend. So this is the sort of general way that you would correct for the wall slip. So this is, as I said, an artifact that you can correct. And there's an analogous process for the circular cross-section capillaries. And there is also a way to correct for slip in rotational instruments as well. A similar idea. In that case, you would, instead of changing channel depth, you would work with, say, parallel plates and then change the gap distance and do multiple measurements at different gaps. So slip can be handled in pretty much every situation if you're able to do that variation in either gap or channel depth. Okay, let's move on to yielding materials. So our example here for a material that would yield is something we've talked about before. So we're looking at a polymer that self-assembles in solution. This is a poloxamer, so it's a tri-block copolymer where the mid-block, due to this extra methyl group, is more hydrophobic, so it will self-assemble under certain conditions. And so, the reason that we can see yielding in this particular formulation is that these have a particular phase diagram depending on temperature and concentration. So if we're at high enough concentration, as we increase temperature, we move into basically a gelled type state. And so this is a type of material that, can support a particular stress before it actually starts to flow, and then can, potentially exhibit this yielding behavior. So what we have then is, well, let's look at the relative viscosity as a function of temperature for different concentrations of our poloxamer. And what we see is as we go up in concentration, so now we're moving, say, along this axis, initially we don't see any unusual behavior as our viscosity increases and then subsequently decreases with increasing temperature. But when we get to high enough concentration, we start seeing some unusual things happening here at this peak region. So presumably what we are doing is, moving through this gel type region and then back out of it when we get this well-behaved behavior, well-behaved system as we increase temperature. So the first sign that something strange is happening is that this is very inconsistent. And although I haven't talked about it too much yet, artifacts typically are inconsistent and give you irreproducible data. That's not always true. There are certain cases where artifacts are surprisingly consistent, but in the case of yielding, I would say that it's tends to be to follow that pattern, that it's an inconsistent response. So what we can expect here is that we have different degrees of yielding depending on our data point here, which gives us this irreproducible behavior in these large error bars. So how can we look more closely into this? And so one thing we can look at are our transient curves. So if you're familiar with actually not just our particular software, but any software should give you the time-dependent behavior. So what we look at then is the stress as a function of time, and we're looking to the point where we get to a steady state, and then we use an average over some time period to actually calculate our viscosity. So what we can see that's typical in yielding materials is that we have this stress overshoot. So when we're at this 30 degrees, let me jump back here. So 30 degrees, our behavior is pretty consistent, and we expect that we're not moving into the gelled region. But then once we go into the 40 degrees, where we think we're in this gelled state, and we have this very inconsistent rheology data that we're getting, and we look at our stress as a function of time, we can see this stress overshoot. And this is commonly observed for materials that are yielding. And in this case, the behavior after the overshoot is fairly consistent, but it's also, a common thing to see very erratic behavior after you go through the stress overshoot, depending on, how much of your material is actually being broken down during the flow process. So this is one other thing that you can look for as the material is yielding. Okay, so the final thing we want to talk about, and unfortunately I don't have data to show you, so this is probably less satisfying to see all the equations, but let's go through this and it'll help you understand, whether you should or should not expect some, viscous or shear induced heating in your system. And then we'll discuss, what that may look like, even though I don't have any example for you. So what happens in terms of this viscous or shear induced heating? So you're shearing your sample, and this sort of mechanical energy then can translate into thermal energy. And if you look at, so we've talked about conservation of momentum, which handles the fluid mechanics, but if you have this viscous heating or viscous dissipation playing a role, then you're going to need to pull in the conservation of energy. So you're going to need an energy balance to handle this. And the term in the energy balance that deals with viscous dissipation looks like this. So it's viscosity times the square of the shear rate at the wall, or the stress at the wall times the shear rate at the wall. So here's, this is our first guiding point as to when we might see shear-induced heating. So it's going to be for high viscosity samples that you can shear at a high rate. Now, as we move through this analysis, that's not the only factor, but if you don't have a lot of information on, the thermal conductivity, say, of your material, and you know that you have a high viscosity material and you're shearing at a very high rate, then you can be on the lookout for this type of artifact. So again, we're going to create a dimensionless group that's going to tell us, or it's going to guide us as to how, whether or not we should be concerned with this. So the first thing I'm going to do is we're going to take this viscous dissipation term, and we want to say, okay, knowing this, what kind of temperature rise do we expect for our sample from this viscous dissipation? And so that's what this is. This is the scaling for the temperature rise that comes from the shear flow. And it's going to, and you can get this if you look more closely at the energy balance. You can get this particular relationship. And what it's going to involve then is the channel depth, and then also, and this expression is specific to our flow channels. You can get equivalent expressions for other geometries, and you can find those in the literature, but this is specific to our rectangular flow channel. So it's going to depend then on thermal conductivity of the fluid, and then also the channel depth. And this is going to be the approximate temperature rise due to viscous dissipation. Now, what's then the other temperature scale that we want to consider, that we want to, look at the proportionality of? And that would be, is how sensitive is your viscosity to temperature? And so to do that, they're defining this in a slightly different way than you typically would. But typically then the viscosity sensitivity with temperature is exponential, and they're using this particular factor beta to say how sensitive is my sample to the viscosity of my sample to temperature. So the temperature rise for a significant viscosity change is going to scale as 1 over beta. And then we define our new dimensionless number, which is the ratio of these two temperature scales. And it gives us, again, it has fluid properties, and then also properties of our flow configuration and our experimental output. So what we find is that, when this particular value is greater than or equal to 1, you should be on the lookout for errors due to viscous heating. And in this case, what's happening is we're creating an inhomogeneous sample because we're having temperature gradients in the flow field. So we're still going to have something close to the correct temperature, near the wall because of the energy transport near the wall. But, in the internal section of the channel, we're going to see, greater variations. And then also, if we're doing, say, a rate sweep, now we're going to enter into a situation where we don't have steady state anymore, because as we pump through the channel at higher and higher rates, we're going to increase the temperature more and more. And so what typically, you see in terms of, experimental outcome here is that because in general, the viscosity drops with increasing temperature, you can have, say, Newtonian samples that will then start appearing non-Newtonian, looking like they're shear thinning, because as you pump at higher and higher rates, the temperature is going higher and higher, and your viscosity will drop. Or in the case of a non-Newtonian fluid that already shear thins, then this will be enhanced further. And so that's typically how it will appear during the course of your experiment. Of course, if you have something unusual like a polymer that actually can have an increased viscosity as you increase the temperature, then you can have, some other types of manifestations of this. But that's, probably not too common of an experiment or an outcome, I don't think. So typically you'll see this unusual thinning or enhanced thinning. Okay, so then the final thing I wanted to point out, because again, I think it's always very important to look at your data critically. And, one way to do this and get a decent amount of information is to look at your shear stress versus shear rate. So don't just look at viscosity versus shear rate. Go ahead and look at it in a different way, because this can be a good indicator of some kind of trouble going on. And this is actually from our Polymers sample, where we believe that the fluid is yielding. And when we look at shear stress as a function of shear rate, one of the signs that we get from this particular plot is that we have this region here where the shear stress is pretty much independent of the shear rate. And this is not this is a sign of a problem. So a homogeneous fluid, as you continuously deform it at a higher and higher rate, you should not see this independence of shear stress as a function of shear rate. You should see more this continuous monotonically increasing shear stress as a function of shear rate. So one of the signs that you have some unusual behavior is this independence of stress on shear rate. And the way this will manifest, if you wanted to look at your viscosity as a function of shear rate curve, is that you'll have a power law of -1. Now, the other thing that you could look out for here, and I don't have an example of this because I haven't actually seen this, but if you have some other strange behavior, you can actually see shear stress decreasing as a function of shear rate. And that's another red flag that something is wrong, because that's not physically possible to have reduced stress as you shear at a higher and higher rate. So if you want to look at shear stress and shear rate as an indicator of things happening, and if there's something strange going on, look for either a decrease in shear stress as a function of shear rate or an independence of the shear stress on shear rate. These are signs that there's some kind of problem going on there. So I think we will stop it there and see if we have any questions. Okay, so it looks like we do have some questions already. So let me read. So we have some questions about if I can elaborate on scale regarding homogeneity and flow, and then also elaborate on length scale. So that's a little vague, but let me try. So in terms of homogeneity, it kind of depends on, you can have different types of homogeneities. You can have homogeneities that are on relatively small length scale that can lead to the wall slip, or you can have, more macroscopic phase separations that, where the length scale of the different phases is on par with, say, the channel depth in our case for our flow channel. So, what I'm talking about is what, in the flow channel, on what length scale do you see these discrepancies? And it can take a fairly small inhomogeneity to give you wall slip. You just need a very thin layer near the wall such that it appears that the bulk of the material is slipping. Or you can also have problems if you have larger length scale inhomogeneities where you have, the length scale of your different phases, for example, is on par with the channel depth in our case. Hopefully that helps. If not, you can type in another question and I will try again. So let's see. Okay, so there's a question about when we calculate the Reynolds number for the extensional rheometer. They're asking what viscosity is it that we use for non-Newtonian fluids with varying viscosity? Is it the zero shear rate viscosity used? Okay, if you go look at sort of the more traditional, this is a slightly tricky question because if you're dealing with a pure extension, so I didn't go into the details about our extensional flow channel. Our extensional flow channel doesn't give you a pure extension. It's a mixed flow. It's because we have, no slip at the walls, you're shearing it as well as, introducing the extensional extension as well. So if you were dealing with pure extensional flow where you had, no stress boundary conditions, I would say that you do use the zero shear rate viscosity. It's a little less clear when we have the mixed flow situation, whether you should use the zero shear rate viscosity or if you should use the viscosity at the shear rate that's being experienced by the material in the flow channel. So I would lean towards using, in our particular case, since it's a mixed flow, using the viscosity at the shear rate that it's experiencing in the flow channel. But if you did in fact have a pure extension with a zero stress boundary condition, then I would use the zero shear rate viscosity. Okay. Okay, so then we have another comment. So someone that does use our extensional channel, stating that they have observed turbulence with polymer solutions, but they were saying that these were elastic in nature and not due to inertia. Okay, so then they gave a reference. So that's interesting. I'll go take a look at that, because that's important to consider. There are some other driving forces that could exist that we didn't talk about. Okay, so the next question is about viscous heating. And it's asking, at what viscosities does this typically happen? So I think you want to look at not just the viscosity, but the product of viscosity and the square of the shear rate, because you can actually measure very high viscosity fluids at low to moderate rates and not have a problem with it. It's really the product there that matters. So yeah, I would consider, I don't want to make the call on viscosity alone. It's really the product of viscosity and shear rate squared. And another question is, can MVROC measure this temperature increase so that we can get some indication that something is going wrong? And yes, you will see, I should have mentioned this, so thank you for asking. When you actually look at your data and take a look at the temperature, which is constantly being monitored and then presented to you, anytime I've seen viscous heating, I have seen a small but detectable increase in temperature that's occurring. So you're not going to know exactly what the temperature of your fluid is, say at the center of the flow channel, because that's not where our temperature sensors are. But you will see a small but real increase in temperature in our system, and I've seen it in rotational systems. So the answer is yes. You'll keep, that's a good point to make. Also look at what your temperature readings are, because you will see things tick up a little bit. It won't be huge, but it will be beyond the the typical control that you see. Okay, so I think let me just go back and review and see if I've got all the questions and give you another minute or so in case someone thinks of something else. And also, while we wait one more minute, as always, in case you're new to our webinars, anyone who registered will get a link eventually to the recording. So, and then everyone who joined us today will get a link to the recording if you wanted to review something again. And of course, you should get contact information too if you want to ask any follow-up questions that you didn't think of during the live session. So I think that's all of the questions. So let me just thank everyone for joining us today, and please keep a lookout for announcements for, oh no, wait, we just, I think, got one coming in here before I conclude. So again, this is a specific question to our instrumentation and temperature monitoring. So can it also detect if the measurement is temperature controlled with thermocube? I'm not sure what you're getting at. So you can operate without temperature control. However, of course, we would recommend, particularly in this case, that you do use the temperature control. Yeah, I'm not sure exactly what you mean by can it detect if the measurement is temperature controlled with the thermocube. If you're looking at the software, it will sort of constantly give you updated status that your temperature has stabilized, and it will show you constant readouts of the temperature. So you can detect, tell that way if you're observing what's happening in the software. You'll get constant updates about stability of your temperature, and it'll constantly report the temperature if you are if the software is in communication with the temperature cube. Okay, so another follow-up then. So the first question about temperature control was assuming that we were operating without temperature control. So if you're going to try to look for viscous heating, I would operate with temperature control, because what we've seen when we operate without temperature control is that just due to the nature of the electronics, we can see a drift in temperature as you do more and more experiments. And so you'll see drift in temperature if you're not using temperature control, which will make it harder to see any fluctuations in temperature that might come from viscous heating. So if you're concerned about viscous heating, I would use temperature control. And if you are using temperature control, the software will make it clear, whether your control is stable, and will give you constant reports of what the temperature is at the location of the sensors. So hopefully that clarifies everything. Okay. So I think that's it. And again, thank you. Be on the lookout for announcements for March's webinar, and hope that you'll join us there. So thanks, and have a good day.